Your meeting. Is there anybody here from outside the meeting? My gosh! I see. All right. And so, well, I'm a professor at the University of Toronto, and my name is John Polanyi, and I have been there for a long time, and I am at a loss to know quite what these slides contain. Just a moment while I switch this machine on. They contain clearly an introduction to what I have spent my professional life studying. And colloquially, it's the molecular dance in chemical reaction, but it does have a technical name, which is reaction dynamics. And I and my contemporaries had the fun of inventing that name. And of course, what the subject is can we learn something about why sometimes molecules collide and separate, and maybe they transferred a little energy, but they transferred no mass, no chemical reaction occurred, and other times they collide and reaction does occur. Well, so these motions of the atoms and molecules in the course of reaction are what my laboratory and others contemporary with it devoted themselves to. And now I'll explain this picture, but I have to point out that I think I should say a little more about the problem. The problem is to get down to the level of these molecules and interrogate them. And what are they doing? Well, they're exchanging partners and liberating energy. So an easy start would be to try to find out what happens to that energy. Energy is just motion. So I'm talking about the same thing as I was talking about a minute ago. And one thing that could happen to the energy released in a chemical reaction is that the products just race apart. And that's called translation. And my friends, particularly a couple, one at Harvard and one at Berkeley, set up crossed molecular beams of chemical reagents and then timed the products to see how fast they were going. Well, I was starting up at the University of Toronto. I didn't feel either clever enough or rich enough to attempt what they were doing, so it took a totally different track, which depended, I mean, my whole interest in the subject depended on the fact that people at Manchester University, where I was trained, told me, this is a hot subject, go for it. So it's very important who you train with. But we didn't try cross-molecular beams. We tried to let the molecules signal to us what they were up to. Well, if the molecule is translating, no signal. If the molecule is vibrating, which is very likely, then it will give off infrared. And if it's rotating, it'll give off a slightly different color of infrared, different wavelength. So, inspired by my stay in Ottawa, I'd been 2 years in Ottawa. Gerhard Herzberg, world's leading spectroscopist, was there at the opposite end of the same building. Inspired by that, and then things I had seen in a couple of years I spent at Princeton, we decided we'll try and detect this infrared from chemical reactions at low pressures. Why low pressures? Because the object of the exercise is to see the products as they are born. And there's, you know, I must watch the time, but there's a question of terminology here which will amuse you. I mean, normally I wouldn't bother with it, but my colleagues, we scientists love tech talk, and they developed this notion that what people like me were studying were nascent molecules. Well, you know, that's it comes from a failure to know the roots of the language. If you go to a hospital and ask to see the nascent babies, they take you into the delivery room because they are in the process of being born. But what you really want to go is to see the newly born babies, and that's a completely different room. And nascent is in 1,000 papers, and it's not the right word. Newborn is what we were looking for. So we had to go to low pressure because at higher pressure, these newborn babies would have hell beat out of them by collisions with other molecules. You have to get them to signal their vibrational and rotational state initially. And we went to a lot of trouble to do that, but trouble isn't enough. We were very lucky. First of all, I was lucky that this was my first student. He was marvelous, and he knew how to run this thing on the left, which is an infrared spectrometer. And the whole essence of the experiment is contained in that little white blob there. That's a little glass container, and the white blob is a bit of asbestos on it. But there, hydrogen atoms formed in this discharge float into here, and from a tube which you can barely see coming from above, we variously put various molecules. One was ozone, because H plus ozone was a reaction we'd heard about from Hertzberg. And we didn't know we were doing something relevant, but we were. And actually the machine as built has a source of infrared here, but we pulled that out and put our chemical reaction there. And Ken Cashin did something else. He found a detector which is housed beneath here, a liquid nitrogen-cooled semiconductor chip. And that was the latest thing at the time. And but for that, I mean, there were many places where we could have disappeared forever and I wouldn't be here before you. And that was one of them, because infrared detectors were very poor, but the military had found these lead sulfide detectors did detect infrared, and they mounted cooled lead sulfide in the nose of Sidewinder missiles, which seek out the jets of jet planes and disappear into the jet, and that is it for the jet. Well, these detectors were classified in the United States, but nobody had got around to classifying them in Canada, and we were in Toronto, there it is, doing this work, and so we could get such a detector. Without that, we would have just seen some boring lump of radiation. With that, we saw, sorry, I'm going the wrong way. We saw this, which is a whole lot of spikes. And each spike has a name which you can derive by getting Hertzberg's textbook and looking it up. And the V tells you its vibrational state, and the J, or something like it, tells you how it's rotating. So there's a huge, rich bit of information here. And actually, even glancing at it, you can see that vibrational states 6, 7, and 8 are populated. That means that this reaction adores making vibration-excited hydroxyl radicals, which Hertzberg had guessed to be the case, because he'd actually stuck his spectrometer up and looked at the sky. And mostly, even from Ottawa, he saw the neon signs in Las Vegas. He had a very sensitive detector. He wasn't interested in the neon signs in Las Vegas, but he saw the lines of neon, and interspersed with them, he saw this. But he didn't know that it was the reaction H plus ozone, because he wasn't present in the upper atmosphere, whereas we were present in the laboratory and knew it was H plus O3. That's what we were mixing. So where did this get us? And now I will speed up, because you're in the right territory. I haven't mastered this thing. It meant that we knew something about the product excitation in one reaction. And in fact, it turned out that we had a generalization, and that's what basic science is about. I don't know whether you, I was only just given the program. You have some talk about science policy here too. So there is something called basic science, and there's something else called applied science, and there's a link between the two, but they are different. Have you had your science policy talk, or shall I give it? Have you had it? Yes? Yes. Okay. Attractive reactions, clearly H plus O3 is one, but there was a much bigger class we found of repulsive reactions where the reagents came together and then, as if a bomb had gone off, the products flew apart. H reacting with chlorine is like that. The HCl comes off with very little vibration, but an awful lot of translation. So, of course, at this point, we rushed off to see our friends at Harvard and Berkeley and say, look, you should see a lot of translation, and you should see it in bunches, because you will see very little translation if there's a lot of vibration, and then you'll see something in between, etc. And they said, we don't see anything of the sort. And so very depressed. I remember sitting at a Gordon conference on the grass and thinking the world was coming to an end. But it turned out they'd made a mistake. And so in the end, the vibration and rotation matched their translation, and we had accounted for the product energy distribution. And then we did the thing that you would expect us to do, which was to think how we could alter the reagent distribution. And so we went, I mean, this is just normal human megalomania. We went from a reaction vessel size of a fist to this thing here, which looks like a steam engine. And the reason for that, apart from the fact that people at last were willing to give us a bit of money, the reason was that we figured we'd have to slam the reagents together. And the way to slam reagents together when they are neutral, uncharged species, not that easy to accelerate them. You do it by having a jet, and you insert your molecule into the jet, and then you let the other molecules scatter and skim off the core of the jet, and you have, for example, translationally hot H atoms, for example. We did it with that. And and then we were able also to get vibration-excited reagents. And you could guess how we did that. We just used our own reaction in a sort of pre-reactor and drifted vibration-excited molecules in, and then brought a second reagent in and saw whether it gobbled up the high vibrational states in preference to the low. So we then had our second finding. And really, you know, my purpose here is not to leave you going from this lecture theatre with some useless information about reaction dynamics. It's just to give you an idea of what basic science looks like, you know, but here's another. To give you an idea of the scale of knowledge which is regarded as being worthy of note. And so, because I'm almost finished the science, we looked at various reagent energies, very hard to read, but the red thing here says vibration, and that was very good, we found, for reactions where the thing had to climb up a hill to form the products, endoergic or endothermic reactions. But translation, which we got out of that huge machine, that was good for promoting reactions where energy is liberated. So now we had some sort of generalization about reaction products. More important, we had a generalization about what sort of reagent motion will enhance reaction. So if somebody wants to steer a reaction, this sort of information is fundamental. They can tinker with the translation or the vibration and steer the reaction. So that really was the chapter which you heard was celebrated so long ago. And that usually is, of course, the end of the story, and I would then go on to science policy or something. But I was very lucky again, because in 1986, that year that I and the person at Harvard, who was Dudley Hirschbach, and the person at Berkeley, who was Y.T. Lee, all met as chemists in Stockholm, the physicists, who I happen to know, but they didn't know we were there, we met outside our lecture theatres, physicists were getting the Nobel Prize for this thing called STM. So we grabbed it. It's perfect for reaction dynamics. It's not easy, but it's perfect. What is it? Well, you take a whisker of metal, as you know, and you study not actually the flow of charge in the normal sense, but the tunneling of charge from the whisker of metal to the surface. And that's what they had done. And tunneling is very sensitive to distance, and so every time their tip passed over a bump consisting of one atom in a crystal down below, they saw an increase in the flow of current. And when they passed that atom, they saw a decrease in the flow of current. You can now resolve atomic features. And here were we, who wouldn't have dreamt of attempting such a thing, but we were very interested in chemical reactions. So this tool has turned out to be very valuable. Whoops, I just am going to give you an indication of what new vistas it opened. First of all, we went back home and put a layer of halide on a crystal of silicon, and of course we found we could write at the atomic level. If you pulsed here with the STM tip, you got 3 chlorine atoms from this chlorobenzene, and then you pulsed here and you got 3 more, and so on. So you are writing in atoms. Well, that's fine, but actually, you know, though we were doing basic science, one is very conscious of applications and very interested in them. And clearly, nanoscience was the hot story. It now, I think, regarded as, you know, one's supposed to boast one is post-nano now, meaning that you've gone to biological, the meso systems. But I'm not post, I'm still nano. And the thing is that you cannot make a device that a human being can use, atom by atom, in under geological time. So there's something wrong here. This writing with the tip is not a good way of making anything. But there was a trick at hand, and that was quite obvious to everybody that the way to build a house at the atomic level was to have sticky bricks, which, when you shake the bag, they fall out and they stick together as a house. So that's called self-assembly. And there's an example of a self-assembled layer, and there's a single circle of self-assembled methyl bromide molecules on silicon 111 phase. Well, but since the molecules had to move across the surface to find each other, they are very mobile. So though you have self-assembled a house, let's say, if you go into it, the house collapses. So that's not the end of the story, it's the beginning. And the next thing to do is to wheel in some chemistry, and that's what's being done here with this flash of light. And we actually imprinted this circle of methyl bromide by photodissociating it, and this was Jody Yang's PhD thesis. These are individual bromine atoms, and with one flash of light, it's multiplexed, you do it all at one time, with one flash of light, the self-assembled trembling pattern has become firmly anchored to the surface. And so this is a molecular scale printing press. Sounds promising, and actually we took out a patent and gave it to the University of Toronto. This is probably unnecessary digression. I'm just going to Cambridge to discuss this with some people there who are speculating about it, but it's here and it's fun. Not everything remains rock solid. I'm going to show you a case that we have published not too long ago. This is a different face of silicon, in which you get these pairs of silicon atoms lying in rows. And if you bleed into your chamber a bit of ethylene, which has a double bond, the double bond opens up and the 2 single bonds attach to adjacent silicons, one here, one here. So now it's stuck. So now you do something which is great fun to do, and we are doing a lot of it, which is, instead of warming things to do reactions, electron induce the reaction. It's also fashionable because people want to use the sun's rays, and the sun produces photoelectrons. Well, actually, we produce our electrons or our holes by bringing the tip, you can see the tip now coming, to the molecule. And the molecule disappears. So, you know, if you aren't a great student, you'd say, well, tough, I mean, it desorbed. and that's not very interesting. But if you're a very good student, you hunt around, and there it is. It's still there. It's just moved. So how the heck could it move over what is actually a very rough surface like this? And in the published work, you'll see it's a very directed motion. What's going on here? And if the people in Cambridge agree with us, it's this. The molecule, when the bond to the surface breaks, it breaks at this point here and starts the molecule doing that, which is both directed and long-range rolling, which is something new. So I would hate to justify all this on the basis of applications. It is a basic science in which one is opportunistic and really can't attend to the next stage where somebody might use it. Not too much, anyway. I'm now going to just wing off into the further reaches of this talk, and that I will be on time in finishing, I think, easily. I say that the basic is to be distinguished from applied, and this actually is a hot subject because governments are very anxious to fudge the issue and to say we'll pick the very best scientists and we'll support them, but then we'll pick from those very best scientists those that are working in areas which are going to add to the gross national product in the next 10 years. And then they're no longer picking the best scientists because they're best scientists. And they are assuming vaguely, if they are thinking, that you can at the same time attend to the requirements of basic science and attend to some customer who has important needs, namely somebody in the world of applied science. You can't serve God and Mammon at the same time effectively. But still, one talks to people who are interested in applications and one is fascinated by them. And so I was going to say that out of this work, which nobody would have supported as a way of producing infrared radiation, well, along came Towns and Shawlow. Actually, literally along came Shawlow into our lab, and they hadn't yet published their laser paper, and he told us about it. And so we saw that this would be a nifty way of forming the medium for a laser, because the trick is you must get excited species in the absence of unexcited. Well, we can do that. Chemical reaction will form vibration-excited products, and put a mirror at each end. Actually, here are the mirrors, somehow. Here we are. There's one mirror. You can't see the other. This is my student, Jochen Wanner. This is the reaction vessel, which had to be designed by a good engineer, so there was good laminar flow. This is the discharge that forms the hydrogen atoms. Chlorine enters at numerous ports above and below. It's a feat of design which we weren't capable of, but Terrell Kuhl was. And out of this came pouring infrared radiation, and quite intense too. And so work that, you know, if the funding agency had been on its toes, would have been turned down on the basis that there was no detector able to see the feeble infrared we were going to look for. We were just bloody lucky. Was in fact able to produce not just an intense, it's actually a much more elaborate story. You just need to have something that's cool rotationally and slightly hot vibrationally, and it lasers like crazy. Well, so people took note. This is my Science and Society section, and long ago the Air Force scaled this up and used it. It was actually, the chemical laser was to be the first line of defense in something that was nicknamed Star Wars. And you heard about Pugwash and so on. It was a debating club among scientists. It still is. It was international. So, you know, for 25 years we had an iron curtain across Europe, but was penetrable by scientists and was penetrated by scientists who went and discussed what should be done so that somebody didn't mistakenly let loose these nuclear weapons, of which there were 70,000, which people were threatening each other with. Now there are only 20,000, but unbelievable destructive power is sitting there waiting for somebody to make a false move. Well, one thing we decided was that missile defense like this, which I suddenly found myself in the front line of, was an illusion because, of course, the missiles that get through are intolerable and represent a disaster which we can't imagine. But then along came President Reagan, and if you ever read the story, you'll probably hear it told backwards, that somehow I got involved in the technology of missile defense and felt pangs of guilt and so on. It isn't that way around. I was warning against missile defense along with my chums in Pugwash for 20 years before Reagan's Star Wars. Anyway, so I debated this subject with Edward Teller, who was the one who persuaded Reagan this was a great idea, and with fateful consequences. Reagan and Gorbachev were really very close to a major arms control agreement, in fact a disarmament agreement, and it all fell down because of this hoax, this destabilizing factor that when one side gets missile defense, it feels somewhat protected, and the other side feels somewhat disarmed. And so they're not in the mood to start destroying their weapons. I say this because, in fact, it is a topic of the future. Prime Minister Harper is showing some interest in collaborating with the United States on missile defense. It would be a foolish move. What else do I have to say to you? Well, by implication, I think I've already said it, that we rely very much on public debate. I just have a couple of pictures. This is somebody who I knew, who was a cosmologist, astronomer really, and it's quite interesting. He wrote a gentle letter to the leader of his country, China, saying, if we had some public debate, not only would we make better decisions, there would be more legitimacy to what the government does, because it's got the imprimatur of those who are being governed. Well, that was enough, because he was a credible guy, a good scientist, was enough that in 1989 he was top of the most wanted list. The students were well down the list compared with him. He fled, luckily got out, sadly died. And my next slide is one you've seen before, and it's just to show you a citizen dealing with his government. Let's see if I can get it to move, though. I have to do this just a moment. Nothing happening here. Just a second. Ah, there. Come down. There we are. Okay, now which button? This one. You will have seen this before, but this chap is just coming back with his groceries from doing his shopping, and he meets this row of tanks. He's dead, I'm sure, too. But he realizes that the tank contains another human being very much like him, and he wants to talk to him. And I don't have the whole of the film. It exists. He actually climbed up on the tank, stuck his head in the turret, and started arguing with the guy who ran the tank. And that's really what I want to recommend to you. I don't want to draw any more morals. Thank you for your attention. That's the end of my talk.
Sorry, are there questions? Let me ask you a question then, since I have the microphone. The question is, Steven Weinberg, sorry I got it wrong. So Steven Weinberg, in last year, in New York's Review of Books, he wrote an article about the crisis of big science. He was particularly talking about the funding of large-scale colliders,
yeah.
in sense. So my question to you, you touched this point very briefly about funding or how government tries to pick winners and losers in a sense. So in your view, do you see some sort of challenge, crisis in that sense? Or would you call it?
Well, you're particularly asking how one picks winners and losers when the entry price is $1 billion or something. Yeah, it's a very, very difficult question because, I mean, my instinct is to say use the same criteria that you use if the entry price is much smaller. I mean, you should only invest if you get returns which are in some way comparable with or commensurable with your investment. So you're entitled to ask a lot in the way of new understanding from a huge investment. But I recognize that, you know, you can't build half of such a device, and so that's what makes it such a difficult problem. And I think probably the world is dealing with it very adequately. I mean, that what is present at CERN and so on is as international as can be, I think, and shows people behaving very rationally and in a civilized way.
Others?
I don't know if I'm tied down. Oh, sorry.
So across the globe, governments are starting to realize the benefits of science diplomacy. With your experience, could you comment on the usefulness?
I think you'll have to hold the microphone a bit closer, yeah.
So could you comment on the usefulness of science as a diplomatic tool?
Sorry?
Could you comment on the usefulness of science as a diplomatic tool? As a tool
the usefulness of science?
As a tool for diplomacy.
It's the last phrase that I'm missing.
Tools, diplomacy.
In diplomacy?
Let me start over.
Yeah. Right.
So across the globe,
Yeah.
governments are starting
Well,
to realize the benefits of science as a diplomatic tool.
Well, I mean, the reason that this one organization, Pugwash, which was mentioned, came into being was to exploit the fact that among a group such as is gathered here, there is some level of trust, and you don't expect to spend your lives checking up on everything that is published in science. You proceed on the basis of trust, and of course anybody who offends against the rules that we as scientists set is outlawed, and quite, you know, finally and fatally. So we do have a society with an extraordinary level of trust for an international society, and that's what we were trying to exploit. And I was involved in doing that in dialogue with people in Russia, because the great danger was between Russia and this continent. And I think that example carries over into other fields. It's not just the nuclear danger, which is still very present. You know, just something that might astonish you. I was talking about this to, well, I needn't go into the details, but I don't know if you've heard of a philosopher called Bertrand Russell. Maybe you have. Some of you have. Well, the greatest philosopher of an earlier century, but that's argumentative. There were other great philosophers. He was very outspoken and took logic where it led and got into terrible trouble as a result. And he was, at core, a pacifist. And yet, in 1947, when the United States was the only country with nuclear weapons, and it seemed as if Stalinist Russia was going to get nuclear weapons, he said in public, I recommend that we, as soon as they get a nuclear weapon, we attack and prevent them from getting nuclear weapons. These people cannot be trusted with nuclear weapons. It was entirely arguable. Now, and lots of people were involved in that debate, but had we followed Bertrand Russell's advice at that point, we would have committed, one of the greatest, not just mistakes, crimes of history, because it was absolutely the wrong thing to do. The Soviet Union disintegrated. History has to be given a chance to unfold. You cannot take such steps with these ghastly weapons. But I just wanted you to realize how much there is to be discussed, because I see that as a template for a discussion that we're having now, which is it legitimate to bomb Iran to prevent Iran from getting nuclear weapons? Iran would be the 10th nation to get nuclear weapons. And in some form or another, I've been through this debate, not 10 times, because I wasn't through it with the United States, but quite a few times. And it would be a terrible mistake to do that. So this is the sort of debate that scientists can perfectly well contribute to. And there are other topics. There is pollution, there is poverty, and lots of things I'm not thinking of. And scientists are involved in these things at various levels, sometimes by invitation at an official level, and in the cases where I've been involved, not by invitation, but by self-organization. And yet, as I was being driven here, I was asked, have you been to Ottawa often? And I realized that I've been to Ottawa to argue with every prime minister, starting with Diefenbaker and including the present one and all the intervening ones. So I've been to Ottawa quite often, and had I not been a scientist, it wouldn't be so likely that that would happen. And of course, if I was a lonely scientist, it wouldn't happen. It's because I belong to a community, as did the guy in the previous slide, which has some credibility, but it has to be careful not to lose it. There he is.
Hi. My question is both general and perhaps personal to you. Where do you draw the line between science as a research and advancement of human knowledge and morality, where you may not necessarily agree that your invention is used in a particular way and you would disagree with it? So how do you go about and say, no, I don't agree my invention be used in this way?
Well, I've never felt that sort of proprietary feeling about any bit of knowledge. First of all, what any one person contributes to the pool of knowledge is absolutely tiny. And my involvement in public debate didn't stem from the fact that I had discovered some small thing or discovered nothing at all. It stemmed from the fact that I was numerate, i.e. I knew something about numbers, I knew something about science, I was a member in good standing of a community of people who were willing to discuss with me. Actually, going in 1960, which was the first time I went to Russia for a political discussion, well, I was a nobody, really. The only reason I went as more or less a Canadian representative was that the people who should have gone were afraid that it might affect their reputation, that they would be tainted as being communist sympathizers. I had no reputation to lose, and so I went. But what I'm trying to say is that the pressure to go came from belonging to a community. And if you are somebody who can read, that's a level of education, and that means that if you come upon something which is written down on a sign saying danger, high voltage, and you're with somebody who can't read, you should read it to them. And so this is just a similar exercise. I mean, we are numerate, we are sort of literate in science, and therefore, I mean, we can't credibly talk about every subject under the sun. I mean, what I say about climate change isn't worth hearing because I haven't read up on it. But I have been involved in discussion of nuclear weapons with people who make nuclear weapons, people who make decisions about nuclear weapons, people who are complacent about nuclear weapons, and people who are very worried about nuclear weapons. And among the complacent are a lot of people, some of them unknowingly influenced by the economic importance of making weapons, but most of them just influenced by a perfectly sensible thought, which is that a lot of hands which might have pulled nuclear triggers have not pulled nuclear triggers because the results would be so absolutely nauseating. But that's not an argument for saying, okay, we will have, as we do now have, several thousand nuclear weapons ready for firing in a matter of minutes. I mean, that's just lunacy. It's habit. It may be vested interest in a sort of funny industry, but it's just heedlessness. And yet, it goes on. That's the situation today. There's no, if it came to such a crisis, there would be no time for anybody to reflect because the warning times are too short.
Yeah.
So I answered you by saying my motivation wasn't feeling that I had contributed something which specifically was good or bad. I'm just telling you the truth. I would find it very hard to say of any basic science that it's intrinsically good or bad. I, after all, have devoted my life to the proposition that it's better to know things than not know them. And so I don't think that anybody who discovers something and teaches people about it has to feel guilt about that, but they should think about the consequences and to be ready to debate them.
What aspects of being a scientist formed your view towards peace and the relationships between countries?
Well, I'm just the same as you. I mean, unfortunately, my travels, which I travel as little as possible because I love to be with my students. I love to try not to have a disaster in my lab, but actually get somewhere. So, but I mean, my travels have taken me to most countries where science is done, and those countries I have the luxury of arriving, not as today being met at the airport, which is quite unnecessary, but finding people who know vaguely what it means to be a scientist and know that I am one, and who are scientists themselves. So the doors are open, and under very difficult circumstances. I mean, during the Cuban Missile Crisis, for example, a bit of debate went on. That was a terrible time. But you don't suddenly say Sakharov is a lunatic or a liar, because you know he's neither of those things. He's dead now, but he was hugely influential physicist in Russia who started by being apolitical, but realized that he could not continue to be.
My question is, what's the biggest change for you after you received a bigger reward, Nobel?
Right. Well, in many ways, not much. I didn't know the answer to your question myself, and I wasn't. You know, anybody who goes around trying to win the Nobel Prize is idiotic because there's so much chance in it. I wasn't aiming to do that, and I was very shocked. But whether it would affect, for example, my enjoyment in doing science, I suppose I did wonder about that. Was I really trying to get that sort of recognition? It turned out I wasn't. That, in fact, it's just as attractive to be doing science today as it was. That's 27 years ago. That's an eternity ago. As for how it affects relationships between somebody who runs a research group and those who are in it, it affects those relationships for about 30 seconds before they realize that their opinion is quite as good as yours and start arguing every point, and that's how life goes on. So it has surprisingly little effect. It's true that I was involved in public debate, for example, on this missile defense question, widely so, and my audiences increased, so that was something rather nice. But of course, if your audience increases, the hazards also increase of making an idiot of yourself. But I would say, on the whole, that it actually, statistically, it's a devastating thing to win a Nobel Prize. I wouldn't recommend it. And no, it finishes people's careers. But I have not spent my time being a Nobel Prize winner. I've spent my time in my laboratory since, and it was very lucky that science was very accommodating, because this fusion of STM with molecular dynamics is a very happy one with a future to it. And so you can survive.
So I have one question also. It's maybe a little personal, but how do you make a balance between your personal life and your scientific and social life? Because as a researcher or a Nobel Prize, I think you should be very busy with the scientific researches, social researches, and sometimes it causes some imbalances in the personal life, especially in the family life. So it's maybe a little personal, but I'm interested.
Well, anybody who starts to get involved in public debate of hot issues is going to do so at some sacrifice to their science. There's no doubt about that. But I think that we all recognize the obligation, and to varying degrees are willing to make that sacrifice. You said that's the social and science balance, and the personal balance, that's a very much harder question, but it wouldn't be personal if I were to talk about it. So I don't think I can enlarge too much on that. No, I mean, you're right, this is an obsessive sort of activity. If you want to stay competitive in a fast-moving field, it makes severe demands. And if at the same time you the only way you can speak publicly about social issues is from a basis of convincing knowledge. And so you have to be willing to spend time on it. Otherwise, you shouldn't do it. The social, this is my social life. You're it. I don't know. I have a wife, I have a family, and I actually have interests which have nothing to do with being a scientist, nothing to do with social obligations. I mean, I love literature, and so at the end of each day I'm reading myself to a state of sufficient exhaustion to sleep. And what I well, I won't give you a list of reading, but don't restrict yourself to contemporary reading, because there's such a marvelous treasure trove of literature in the English language, and that means a lot to me. So that's why it was such a pleasure to listen to the previous speaker, who clearly sees the value of language. And in these meetings with Russian scientists, by the way one calmed things down when things were excited was that one said, well, it must have been a mistake in translation, and so the translator was thereupon required to say in Russian, it must have been a mistake in translation, and but that calmed everybody. But communication is important, and I'm so delighted that you both found a speaker to speak so well on it, and that you wanted to do so. You obviously received him very warmly, and you were right. It matters.
I
actually had a comment to make on your talk, because yesterday it was the 50th anniversary of the sort of boring building in which I work. So I had to give a talk, and so I wrote the talk, and I followed all your rules, and every sentence was sort of attached to the following one. But it was a half-hour talk, so it's a very highly articulated structure. And then I thought, I'm not going to use a text. I'm just going to ad-lib it. But I had to make a list of the points that I had made. And so I had to read what I had written and then throw out the text. I had to read it with a totally different eye, which was to find out the logic which actually made the whole thing work. And I mean, one important thing if you do that is don't digress, because you can get into an alley from which there's no escape. But I survived.
It's my sense that Canadian scientists like to stay out of public discussion. Is that your sense as well? And if it is that good, bad? How can we improve it in either direction?
Was it your opening statement that Canadian scientists stay out?
Yeah.
Yes. Well, I would think that, you know, is potentially disastrous. I think that we do suffer from the fact that as a community we don't have enough of a voice, because if you rely on the odd person who's talkative like myself, you don't get a strong enough response. I mean, if the government says, oh, we're going to get industry from now on to tell NRC labs what research to do, people who have been at the interface between science and application should speak up and say, it's not easy to make that bridge. Let NRC labs talk to the government. There was not nearly enough response, and the question of the funding of basic science in this country, the scientists, since we don't have a journal, for example, or the electronic equivalent of it, we don't have a loud enough voice. And we make pious remarks about basic science, but in fact, to do basic science at the international cutting edge in this country, we are making it incredibly difficult, if not impossible, because you get a tiny grant, and if you're very, very good, it may be 100,000 a year, maybe even 150,000. So now you have 3 or 4 people in your laboratory and you're supposed to compete on the world stage. You can't do it. So what you do, you get some other funds which are targeted for particular applications. And so now you are trying to do two different things simultaneously. Or there are some countries that actually have a strong history in basic science, like Germany, the United States, Britain. They actually do have a lobby for basic science. We should try and construct one.
Does that mean that you're critical of groups like the Canadian Association of Physics?
Am I critical of the Canadian Association of Physics?
Groups that already exist. Do you think that groups that already exist could do more, or that we need newer bodies?
I'm sure they could do more, yes. I don't know the group you're talking about, but I think that we're absolute cowards when it comes to commenting on government policy. And, but you do need to band together to do that, because individuals are too exposed. I mean, you can't at one moment bite the hand and then the next moment go and beg some money. So, but you can do that collectively, and we should. And it's actually hard to do in Canada, because it means, well, I mean, Britain looks back to Newton, Faraday, etc. I won't go through the whole rigmarole, but Germany has a strong history in basic science. So you can make the argument that there is something precious here which has sustained the country for 100 years or longer. You can't as easily make the argument here. And we are not making the argument that basic science is essential to the quality of applied science, and basic science is an investment in the future of this country, and this country should have a great future. We shouldn't mortgage it. And so, yes, I do find fault with all of us as a community in Canada in being too much pussycats.
So I think we are running out of time. So let's thank Professor Polanyi.